At the end of this video, you should be able to recognize examples of projectile motion, describe the path of a projectile as a parabola, and resolve vectors into their components and apply the kinematic equations to solve problems involving projectile motion. Chapter 3, Section 3, Projectile Motion, Two-Dimensional Motion. Previously, we showed how quantities such as displacement and velocity were vectors that could be resolved into components. In this section, these components will be used to understand and predict the motion of objects thrown into the air. Use of components avoids vector multiplication. How can you know the displacement, velocity, and acceleration of a ball at any point in time during its flight? All of the kinematic equations could be rewritten in terms of vector quantities. However, when an object is propelled into the air in a direction other than straight up or down, the velocity, acceleration, and displacement of the object do not all point in the same direction. This makes the vector forms of the equations difficult to solve. One way to deal with these situations is to avoid using the complicated vector forms of the equations altogether. Instead, apply the technique of resolving vectors into components. Then, you can apply the simpler one-dimensional forms of the equations for each component. Finally, you can recombine the components to determine the resultant. Components simplify projectile motion. When a long jumper approaches his jump, he runs along a straight line, which can be called the x-axis. When he jumps, as is shown in figure 3.1 on the screen now, his velocity has both horizontal and vertical components. Movement in this plane can be depicted by using both the x and y axes. Note that in figure 3.2b on the screen now, a jumper's velocity vector is resolved into its two vector components. This way, the jumper's motion can be analyzed using the kinematic equations applied in one direction at a time. In this section, we will focus on the form of two-dimensional motion called projectile motion. Objects that are thrown or launched into the air and are subject to gravity are called projectiles. Some examples of projectiles are softballs, footballs, and arrows when they are projected through the air. Even a long jumper can be considered a projectile. Projectiles follow parabolic trajectories. The path of a projectile is a curve called a parabola, as is shown in figure 3.3a on the screen now. Many people mistakenly think that projectiles eventually fall straight down in much the same way that a cartoon character does after running off of a cliff. But if an object has an initial horizontal velocity, there will be horizontal motion throughout the flight of the projectile. Note that for the purposes of samples and exercise in this course, the horizontal velocity of projectiles will be considered constant. This velocity would not be constant if we accounted for air resistance. With air resistance, projectiles slow down as they collide with air particles, as is shown in figure 3.3b. Projectile motion is free fall with an initial horizontal velocity. To understand the motion of a projectile, first examine figure 3.4 on the screen now. The red ball was dropped at the same instant the yellow ball was launched horizontally. If air resistance is disregarded, both balls hit the ground at the same time. By examining each ball's position in relation to the horizontal lines and to one another, we see that the two balls fall at the same rate. This may seem impossible because one is given an initial velocity and the other begins from rest. But if the motion is analyzed one component at a time, it makes sense. First, consider the red ball that falls straight down. It has no motion in the horizontal direction. In the vertical direction, it starts from rest, where v sub yi is equal to 0 meters per second, and it proceeds in free fall. Thus, the kinematic equations from the chapter Motion in One Dimension can be applied to analyze the vertical motion of a falling ball, as is shown here. Note that on Earth's surface, the acceleration, a sub y, will equal negative g, which is negative 9.81 meters per second squared, because only the vertical component of acceleration is free fall acceleration. Note also that delta y is negative. Now consider the components of motion of the yellow ball that is launched, again in figure 3.4 on the screen now. This ball undergoes the same horizontal displacement during each time interval. This means that the ball's horizontal velocity remains constant, if air resistance is assumed to be negligible. Thus, when the kinematic equations are used to analyze the horizontal motion of a projectile, the initial horizontal velocity is equal to the horizontal velocity throughout the projectile's flight. A projectile's horizontal motion is described by the equation at the bottom of your screen now. Next, consider the initial motion of the launched ball, again in figure 3.4 on a previous slide. Despite having an initial horizontal velocity, the launched ball has no initial velocity in the vertical direction. Just like the red ball that falls straight down, the launched yellow ball is in free fall. The vertical motion of the launched yellow ball is described by the same free fall equations. In any time interval, the launched ball undergoes the same vertical displacement as the ball that falls straight down. For this reason, both balls reach the ground at the same time. To find the velocity of a projectile at any point during its flight, find the vector that has the known components. Specifically, use the Pythagorean theorem to find the magnitude of the velocity, and use the tangent function to find the direction of the velocity.
Projectile motion describes the motion of objects that are in free fall but have an initial horizontal velocity. Both balls are released at the same time and fall with the same downward acceleration. The initial horizontal velocity of the yellow ball does not affect its vertical displacement. As the ball leaves the pitcher's hand, it has a constant horizontal velocity. The force of gravity acts on the ball and accelerates it downward, causing its vertical velocity to increase. The two motions cause the ball to move in a curved path, known as a parabola. Air resistance changes the path of a projectile. When traveling through Earth's atmosphere, the projectile's path is not a parabola.
Use components to analyze objects launched at an angle. Let us examine a case in which a projectile is launched at an angle to the horizontal, as shown in figure 3.5 on the screen now. The projectile has an initial vertical component of velocity as well as a horizontal component of velocity. Suppose the initial velocity vector makes an angle theta with the horizontal. Again, to analyze the motion of such a projectile, you must resolve the initial velocity vector into its components. The sine and cosine functions can be used to find the horizontal and vertical components of the initial velocity. We see that v sub xi is equal to v sub I cosine theta, and v sub yi is equal to v sub I sine theta. We can substitute these values for v sub xi and v sub yi into the kinematic equations to obtain a set of equations that can be used to analyze the motion of a projectile launched at an angle, as is shown on the screen here. As we have seen, the velocity of a projectile launched at an angle to the ground has both horizontal and vertical components. This vertical motion is similar to that of an object that has been thrown straight up with an initial velocity. At this point, you should be able to recognize examples of projectile motion, describe the path of a projectile as a parabola, and resolve vectors into their components and apply the kinematic equations to solve problems involving projectile motion.